I have some slides. Okay, I'm sorry. I'm receiving mails and things like that, so I'm a little bit distracted, but I'm going to concentrate myself. So I'm going to share, and how am I going to share that? Share here. So it's loading.
Yes. Okay.
So
we already see a slide on green manufacturing, new borders for industry. I think it's okay.
No, it's not okay.
No? It's okay. So
no, that's not okay. That's the first one. I'm going.
Okay, okay.
No, that's not okay. I'm sorry. I'm going to stop it. I'm going to stop it and share. Stop presenting. And I'm going to do the sharing in another way. I believe you can see my presentation.
Yes.
Yes?
It's
That's
okay.
the right one. The other one was the first one. So that's a seminar. Christina already mentioned my name. You have here my mail, and I was challenged to say some words. Seminar on green manufacturing, and I titled it "Cases," or I would say a case in engineering design for sustainability. Those slides you already know. Those are the same from the last presentation. So what sustainable manufacturing is the design of human and industrial systems to ensure that humankind use of natural resources do not lead to diminish the quality of life due to losses in future economic opportunities or to adverse impacts on social conditions, on the human health, and on the environment. And other definitions mention that sustainable manufacturing is the creation of products that use processes that minimize the negative impacts, conserve energy and natural resources, and are safe for everyone around the product, and of course are economically sound. The role of manufacturing industry in a sustainable system, it means that it's a complex problem because I need to deal with manufacturing and the socio-economical system, but I need to deal also with the environmental system and to take care and to consider all the flows of materials and energy along those two different systems in a sustainable way, in a way that the future is not compromised. Also, I introduce here also that same slide because frequently, especially when you're talking about SMEs, engineers in those companies, and those companies consider that green manufacturing is something that is not for now, it's for the future. But in fact, I consider that in a very short time, I would say, future, yes, but not long future, the regulation and legislative proposals that will come from the European Commission will lead companies being taxed on their carbon footprint. And even if that taxation might be for some industrial sectors, of course, SMEs are included in complex supply chains, and they are going to be impacted by those taxes. And those taxes and the European Commission will push industries towards a circular economy, establishing rules and extending producer responsibility for optimizing, for companies to optimize their waste management and reach zero waste or zero emissions. So that's something that every company needs to deal with. And here I will begin my new presentation on life cycle engineering. And life cycle engineering is some kind of an umbrella, a concept that includes several things, and sometimes it appears in the industry with several objectives that all of them can be included in that concept of life cycle engineering. Minimization of pollution, minimization of waste, social concerns, eco-design, green design, product life cycle, resource conservation, lots of terms that sometimes they are not different, they are the same, sometimes they are slightly different, but all of them are included in what you call the life cycle engineering, which is not a new concept. It emerged for the first time in the 90s. So for Altin, especially Altin, that work a lot on that concept, and they consider that life cycle engineering is the art of designing the product life cycle through choices about product concept, structure, materials, and processes. And in fact, I consider that it's not possible to have an efficient and an efficient way of deal with green manufacturing if you do not deal with the design of the products that you are going to manufacture. So if you only consider that you are going to manufacturing according to a certain design that is already frozen and completely frozen, of course, you can increase the efficiency and the environmental efficiency of the manufacturing process, but everything in terms of the product is already frozen. And so what you can say is, okay, I can deal with efficiency, but I cannot redesign the product life cycle and consider that I want a product life cycle that must be designed for the environment, for the economics, and for social issues. Of course, there are other definitions of life cycle engineering. Some of the authors or some call it a decision-making methodology that considers at the design stage the performance of the product, the environmental impacts of the product, and the cost requirements of the product. There is no single definition, but there is always a common principle. With life cycle engineering deals with the extension of the design horizon. So that is the enlargement of the design scope from the product concept and the product geometry and the material selection to the design of the product for all its life cycle stages in a systemic way. If you want to have products with reduced environmental impacts, okay, the only way to be efficient on that is to design for the life cycle, considering all the stages from cradle to grave. Okay, based on those definitions, I decided to introduce here a case study that I worked with some years ago that I consider was something that that we introduced the concepts of life cycle engineering methodology, especially applied to the material selection for the life cycle. This is a real case with a real product, and the objective was to select analyze, and compare different metallical solutions for designing and producing and using an automobile front fender based on technological, economical, and environmental criteria within a life cycle perspective, from the design to the dismantling, disassembling, and disposal. Okay, so the objective here was a challenge that was introduced by Volkswagen, by one of the factories of Volkswagen, an OEM of Volkswagen. And the objective was to compare different solutions for the body of the car, dealing with different metallical solutions or plastic solutions based on polymers, composites or simple polymers. Here I'm going only to present the metallical solutions. So based on that, we consider that to begin the analysis, we should identify in a very preliminary phase a set of metallical materials that can be based on the experience and knowledge, empirical knowledge existing in the sector, to be able to select a set of materials. I call it candidate materials. I don't know if you can see my mouse, to select some candidate materials that seem to be very good options for the analysis. And so in that solution, what we've done is to consider what are the requirements and to define the requirements and the relative importance of those requirements, the characteristics that the fender must have. So we define 5 requirements for the fender, independent of the materials they are made of, that the fender must be able to accomplish. So be resistant, be light, allow forming processes, be stiff, allow class A finish. And then we identify the engineering properties. We are engineers, so we don't know what be light is. So you need to identify the engineering properties relevant to carry out the requirements. And here we have, I don't know, 8 or 10 engineering requirements that you can measure, that you can make calculations with, that are related with the requirements that the fender must accomplish. And we can correlate the requirements with the engineering properties. That's nothing new. That's something that engineering designers are used to do it, to understand how are you going to achieve the requirements that the fender must have. Here I have 15 points that it was empirically based on knowledge, based on experience, distributed among the different engineering properties. And based on that and some calculations, simple calculations, we can achieve the importance score for each property. So here, in that case, I can understand that, for example, the yield strength is much more important. It's much more important than the density of material. Okay, so I have a set of engineering properties that have their importance, and of course, their importance is not the same among them. Okay, then I identify a set of candidate materials based on expertise and experience was identified. Here I have 4 materials. Okay, some of them are steels, some of them are aluminiums. I don't think it's not. I don't have here all of them, all the ones that were identified, and of course, for those materials, we collect the numerical values of the relevant properties to achieve the fender requirements, the functions that the fender must accomplish. Okay. And based on that, and some calculations, of course, so they need to the values of the properties need to be dimensionalized, and they need to be pondered and weighted according to the property weight that we identify. So it's possible to identify a weight material index for each material. So in that situation in which I only have 4 materials, we can identify that the steel, the high strength steel, Decol 1000 DP is the one that in terms of accomplish the requirements seems to be the best one. Why? Because the weight material index is the highest one. Okay? So based on those weight material index, it's possible to select materials for further analysis. Don't forget that here it's a very preliminary analysis. So the set of materials that were selected for the fender, I have here the first one and their properties. I have here the first one, which is the current material. Don't forget that the automobile was already in production, so the fender was being produced based on a certain mill steel. Okay, we select 2 high-strength steels with different yield strengths. Okay, quite different, and ultimate strengths quite different, and 3 aluminum alloys. Okay, 6000 class, a 2000 class, and a very special alloy of aluminum alloy that I don't remember anymore what it is. Those are commercial materials available to be used in a stamping line in the automobile factory. So, having the selection of the set of materials that seem to be very good materials to be analyzed, and the current one also, we can go on the selection of these, which materials from that preliminary set are the best ones based on technological, economical, and environmental performance of the materials. Okay, so the first phase is the estimation of part features. Okay, because if the material changes, and it changes significantly in terms of material properties, engineering properties of material, maybe the design of the part needs to be redone, changed. Okay. Afterwards, we can estimate the part costs and the environmental impacts based on process models. And then selection of material, but the best material, selection of the best material, considering in an integrated way criteria of performance, technical performance, economical performance, and environmental performance in an integrated way. Because as you know, and you are going to see that, the best material in terms of technological performance might be completely different from the low-cost material or from the material that introduces the lowest environmental impact. So those 3 criteria need to be analyzed altogether. So in terms of the first phase, which is the estimation of the part features, if you change the material, it is expected that some part features might be changed. And in fact, that's the case. But the current design of the vehicle predefines and freezes already the fender interface with the car body system and the fender aesthetics. So for the designers dealing with that case, it was not allowed to change the interface between the fender and the car, and it was not possible to change the fender aesthetics, how it looks like. Okay, because the car is already produced and in production and is running and out there. So the only features that we can change according to the materials that are being analyzed is the thickness. Thickness is the only design feature of the fender that can be changed. So a certain engineering analysis was done for the 6 candidate materials, 3 steels and 3 aluminums. One of the steels is the current one. And the design thickness was recalculated for those materials. Okay, so the current thickness of the fender in production is 0.65. Okay, and if you use high strength steel, the thickness can be reduced. Okay, and in aluminum, the thickness increases. Okay, it was considered a safety factor because that analysis was a preliminary one, and so to be in the safe side of the analysis, we consider that even if the thickness calculated according to finite elements software was different, it was introduced a safety factor of 20% higher to increase the thickness of the fender. Another thing that I would like you to consider is that for steel 3, the third steel, the one with high performance in terms of engineering properties, the thickness that we need to accomplish the functionality is 0.35 millimeters. However, we noticed that in commercial terms, that thickness was not available. There is no coil that we can be commercially acquired with that thickness. The smallest one was 0.5. Okay, so we use in our analysis both figures. 0.35 is the minimum required. 0.5 is the commercially available thickness for that material. Okay, so now we know the new design of the part of the fender. So you can go to the manufacturing process flow. And we collect the stamping, the process flow of that part. It's a simple one in which steel coil is introduced. There is a first step with blanking, in which blanks are generated, then they are stored, then they are washed, then they are stamping with a complex stamping process with 6 stations, I must say. And then the outcome of that stamping process, there is a significant parts that do not that have defects. Some of them need finishing, rework, and at the end, the fenders are produced and ready for the painting process to be assembled in the body, in the car body, and then to be painted in a coating line. Okay, I must say that the assembly process and the coating process was not considered in the analysis. Why? Because it was considered that those 2 steps of the manufacturing process do not change due to the change in those materials. So if it's the different steel or if it's an aluminum, we consider that those process assembly and coating will not change, so it doesn't impact any comparison between the materials. And then a process-based model was developed to consider for each process of the life cycle phase, but I must say that the most complex is the manufacturing, to convert inputs into outputs in which we can understand which are the resources that are consumed, what are the resources that are required, what are the emissions, what are the energy flows, everything. And if you know all the materials and all the flows and all the requirements that are needed, I can convert those requirements, those emissions, those consumptions into costs or into environmental impacts, depending on the model that I'm going to use. In terms of the manufacturing process, here you have a snapshot of the flow of steel materials, of raw materials, not steel materials. In that case is the current process that is already implemented in the OEM. And so we are having here a mill steel, which we call ST1. Okay, and those are real numbers that we collect in the factory. So the inputs of coil is around 600,000 kilos per year. Okay, and the output in terms of fenders is 100,000 fenders, right fender and left fender, which signifies, which means that in terms of output, what I have here in terms of mass of the final fenders is around 160,000 kilos of steel per year. Okay, and that was a first surprise when I performed those calculations, because almost 74% of the raw material input becomes scrap. Okay, and it becomes scrap at different parts of the process. In terms of blanking, in the blanking step, I have almost 3 tons of scrap. Okay, but most of the scrap arises from the stamping process, and it's not because of the rejection. It's not because of non-quality. In fact, because of non-quality, I only have in the blanking 300 kilos of rejects, and in the stamping, I only have 83 kilos of rejects. Okay? More here, that value, okay, that value here, it's not okay. So the point here is we have in that manufacturing process, we have a lot of scrap that comes from technological scrap. So it's a scrap that comes from the technology. In terms of manufacturing process, only in the manufacturing process, this is not the life cycle cost, this is only the cost of the manufacturing, it was possible to identify what is the importance of the tooling cost, energy cost, labor cost, material cost. And in fact, this is for steel 1, steel 3, and aluminum 1. And what we come up with is that the cost structure is very similar among the different materials. But you come up with a conclusion that material cost is almost 1/3 of the total cost in manufacturing. And in the process, that has almost 74% of scrap. So 74% of the material that I buy are eliminated in the process through scrap due to the technologies that are being used and the way those technologies are being used. So, because the material cost is so important, 1/3 of the manufacturing cost is material. We can say that for different steels and for one aluminum, the part material cost reduces from steel 1 to steel 3, but increases significantly for the aluminum. Okay? If you use the minimum required thickness for the steel 3. If you use the minimum available thickness, that's not the same. So that's a conclusion in which the commercial availability of material can have a significant impact on the costs of the components that I'm being used. It signifies that I'm going to use more material that is needed with more cost and for sure with more environmental impacts. Okay, so that's the trigger for an analysis that was done in terms of reduce the waste of material that was introduced in the process due to a not so efficient, we can create a process using stamping process, but in which the waste of material can be reduced. So that's the geometry of the initial blank geometry in the blanking step. And that's the shape of the blank and part geometry after the first stamping operation. Don't forget that the stamping process has 6 steps, 6 stamping stations, I would say. And what you consider is that it's possible to have, with a more complex tool for sure, but it's possible to have in the same stamping, in the same blanking, to have both fenders, the right and the left fenders. And with that, we have an area reduction of the blanking, and for sure, with that area reduction, we have also a reduction in the material input in the process. Of course, to do that, we need to introduce some analysis of the stamping process with finite, here you have the finite limit diagrams of the current stamping and alternative 1, and alternative A, in which the both right and the left fender are just a mirror one of the other in the same blanking, and in alternative 2 they are not the mirror, but they are positioned using increasing or intending to increase the efficiency of the use of the material. Okay, so in that situation, the unit fabrication cost with 3 steels and 1 aluminum, when you compare the original blanking and the situation in which we have only 1 blank for the right and left fender, it's compared. And for sure, because we are using less material, the unit fabrication cost is going to reduce. Okay? It's a small reduction, but it's significant. Don't forget that you are going to produce 100,000 fenders per year. Okay, so now we can look at the life cycle assessment. We have all the data for that. We have the geometry of the part. We have all the data in terms of the process with the flows of energy, material, water, emissions. whatever you can consider. Okay, so CIMA Pro and Eco Event database were used for environmental evaluation, following the the Eco Indicator 99. Okay, here in the left part, we have the life cycle cost, not the manufacturing cost. Of course, the manufacturing cost is here in the fender production. Okay, but we have the cost of the material acquisition, fender production, fender use, okay, and dismantling. And if you can see, in the case of high strength steels or aluminum, because they have a low density, okay, we are going to use a lower thickness and they have a lower density. The fender use as a reduced life cycle cost just because the consumption of fuel is reduced. And then you have the dismantling, okay? And the dismantling and the cost of the dismantling and the positive income of the recycle of steel or aluminum. And on the right side of the slide, you have the environmental impacts. So Eco Indicator 99. Okay? And here we have a very interesting conclusion in which the high strength steel ST3, the one with the higher performance in terms of engineering properties, has a reduced environmental impact. Even if, when you consider the life cycle cost, it has for the life cycle the highest cost. So even though the fender production stage for steel 3 results in larger cost, it performs quite better for the overall environmental impact. Okay, so we have different materials, we have different technological performances, we have different cost performance, economical performance, and we have different environmental performance. And the best material, according to the 3 criteria, are not the same. So which one to select? Okay. So according to specific conditions, we have 6 materials, we have the technical performance for each one, the economical evaluation for each one, the environmental evaluation for each one, but I need a global evaluation. I don't need the best one for each of those criteria. So the proposal here is to create a ternary diagram, okay, with 3 axes. It's a ternary diagram in which, in the first axis, we consider the importance that the company, that the designer, that the design team wants to introduce to the cost dimension. And it changes from 0 to 100%. In the second axis, we have the importance that you want to introduce to the technical performance or technological performance or functional performance. Okay? And in the third axis, we have the environmental impact. Okay? We don't have here the values of the cost. Okay? What we have in the axis is the importance that you want to attribute to each of those criteria. And of course, the sum of the importance that you introduce, that you want to give to the technical, economical, and environmental performance must sum 100%. Okay? That ternary diagram allows us to map the best design materials, the best materials for all the combinations of the importance that you want to give. The decision depends on the company strategy or the design team strategy, whatever you can call. So in that diagram, what I have here 3 materials that are the best materials. Okay, only 3 materials seem to be the best materials. Don't forget that I was analyzing 6. 3 of those materials are never best solutions, but 3 of those materials can be best solutions depending on the importance that you want to attribute to the technical performance, to the economical performance, or to the environmental performance. An example, imagine that you want to introduce an importance of 10% to the environment, 50% to the cost, and 40% to the technical performance. Okay, it seems more or less something that seems okay. It's a low importance that I want to give to the environment. Okay, I want to give a very a significant importance to the cost. And so I go to the diagram, I represent here the weights, and I arrive to the point B. And so if the importance that I want to give to the 3 dimensions are the first one, 10, 50, and 40%, then the best material is material 2. But if I don't want to give any importance to the environment, I don't care with the environment, I only care with the cost and slightly with performance, in that situation, material 3 is the best one. And if I want to give a significant importance to the environment, okay, and a low performance to the cost and a good performance to the technical issues, so I will select the best materials, material 1. So the best materials depends on the importance that I want to give to the different dimensions of the analysis. In terms of results for the vendor, okay, what I can say is that if I use the commercially available thickness for the high strength steel ST3, so in that situation, only steels appear as best solutions. Steel 1, it's the current one, the mill steel, steel 2, or steel 3. And of course, steel 3 appears here when costs are important and performance are important. Mill steel appears here when costs are important and performance is not so important. Okay, but I can ask, will the solution be different if instead of using the available commercial thickness, I can ask to my supplier for a specific thickness of 0.35 millimeters? Okay, yes. If steel 3, I'm sorry, this is not correct. If with the minimum thickness that I need, even if it exists with a potential 10% increase in costs of the raw material cost, in that situation, steel 2 disappears. This is not steel 2, this is steel 3. This is an error, okay? This is the green one. So it's steel 3, not steel 2. I can change it, I think, like that. So steel 2 in that situation is never a good option or a best option. Okay? And another analysis that I can say is that the process model in the material production for steels we look at the best practices in the aluminum industry, and we realize that if you want to buy aluminum coil, what you know is that the production of aluminum is normally done with 20 to 30% of secondary aluminum, because there is no sufficient available aluminum in the recycle market. Okay? That's not the same with steel, in which 70% of the new steel is produced with secondary steel that comes from the recycling of old steel. But if you consider a future scenario in which 70% recycled aluminum is introduced in the production of new aluminum, okay? Even if I'm using steel 3 with the commercially available thickness, in that situation, okay, aluminum 2 is going to appear with a huge area of being the best solution. Okay? So analyses like that are possible to be done in which, from a set of candidate materials that we can select for a particular application, we launch a comparison process which include the technical, functional requirements of the material, the economical and environmental impacts all over the product lifecycle. Okay? The performance of the candidate materials over the 3 dimensions is calculated based on a technical evaluation, life cycle cost analysis, and a life cycle environmental assessment. Okay? And the best material domains are plotted in a ternary space, in a ternary diagram, allowing the best solutions and to understand what are the best materials for the different applications, for the importance that I want to introduce to the different criteria, to the 3 criteria. Okay? I think I took a little bit more time than necessary, but I conclude. I don't know if you have questions. It's lots of information, but the message is it's very difficult to have good solutions in terms of green manufacturing when you don't have a word to say on the product design. Of course, you can be efficient, but it's only a question of efficiency. Here, it's not only a question of efficiency, it's also a question of efficiency, but it's a question of select the materials according not only which material is the best one or the lower cost solution, but is the best one, is the lower cost solution, and the environmental best material. And of course, the best in each dimension is not the same. So I need to create a way to integrate and to understand the design space of the materials or of the technologies. What was done with the materials, we can say and do the same kind of analysis for different technologies to accomplish a similar product or a product with similar functionalities. Thank you. I don't know if there are questions, too much information.
Thank you, Professor Elsa. Once again, is the right moment to do the questions to Professor Elsa. I think it's a good opportunity to clarify some issues about it. As Professor Elsa said, the future is today, and I think we have a long journey to be more fit with the study of design for design for the sustainability. Of course, we have also a national project that will be finished at the end of this month, S4 Plus. And in this project, we have also the opportunity to study and to work in the process and design to improve, of course, the engineering and also the production, and to be to have more products more sustainable. So I don't know if the people are here have a question to Professor Elsa Henriques.
I must say that this is a real case. Of course, I didn't present all the data. There is a significant amount of data, and this is a real case in which an industrial company was intending to create awareness of changing the material of the car, of the body, of the car body. Of course, you use the fender as a component, but it's not only the fender, and to understand what are the benefits and to create awareness in terms of the functionality, the technical performance, the cost impact, and the environmental impact of using different metallic solutions.
Yes, very interesting, your presentation. So, questions? I think people are shy. I don't know if Rui Tocha, I don't know if Rui Tocha, because I think Rui Tocha have a question to Professor Elsa, but maybe it's in Ireland.
I think he's no more here because he was in the car, wasn't it? Wasn't it?
Yes, it's true. It's true.
So maybe the connection.
Yes, the connection is not very good. So maybe if no have any questions, so I would like to thank you everyone that presenting this in this webinar, and special to Professor Elsa Henriques for her availability to spend this time with us. We know that is very busy. Is a reference in Portugal in these technical areas, and for us it's always a pleasure to meet with her and to listen and their knowledge about these areas. It's very kind for your time. Thank you again. So I think, I don't know if my colleague Katerina want to say something. It's okay, Katerina?
Yes.
Okay.
Yes. Thank you, Professor Elsa.
Thank you.
For all people that will be present here. Thank you again.
Thank you.
Bye. Have a nice day and
Thank you.
a
Bye.
nice week. Thank you.